Hi, my name is Jim Williams and I'm here to talk about settling time in the LTC 2757 18-bit D/A converter. Customers are interested in this measurement, so we decided to take it. It's a difficult measurement. 18 bits is 4 parts per million, which is about 37 microvolts at 10 volts full scale. We decided to go for broke and go for a part per million, which is 10 microvolts. As long as it was hard, we made it harder. What do I mean by settling time? How do we define settling time? There are 3 major components to settling time once the DAC input bits all go high. There's delay time, which is simply propagation delay. The D/A doesn't do anything. Then it wakes up and slews at its maximum rate of speed. And then finally, it rings a little bit before it settles to its final value. Those 3 components make up the total length of the settling time of the D/A converter. How do we measure that to a part per million? This is a very conceptual D/A settling time measurement scheme. We apply a digital input to the DAC, which is summed with a DC reference and brought out to a switch. At the summing point, you should read 0 volts when the D/A converter is settled. During the time the D/A is unsettled or slewing, you have large signal swings at this node which will saturate the oscilloscope, promoting bad measurement. We put a switch here which is delayed in its turn on from the digital input, opens the switch. The switch stays open during DAC slewing. When we very nearly settled, we close the switch and allow the oscilloscope to read the settle signal without introducing any overload to the scope. The requirements for the settling switch are stringent. It must not pass any feed-through or alien components into the signal channel, or they'll masquerade as settling time artifacts. Now we get into a little more detail of the measurement scheme. This is pretty much the same as the last slide. We've put the residue amplifier in front of another triangle. This sample gate triangle takes the place of the switch. It's really a transconductance controlled amplifier, which is controlled by the sample command pulse, which comes ultimately from the digital input through this sample window generator, which is a variable delay in time. So we're going to have on channel 1 the time-corrected input step, and on channel 2 the settle signature. Here's a picture of what comes out of this measurement. This is the time-corrected input pulse, and this is at 25 microvolts per division. That's about 2 ppm per division, the settle residue of the D/A converter. So this signal has come down from 10 volts through the ceiling. We turn on the sample gate at this point right here, and we catch the last 7 or 8 microseconds of settling in the D/A converter. This is a plot of the capabilities of the settling time described in application note 120. This is the best you can do if you had an ideal DAC. From about 12 bits to about 16 bits, you're limited by sample command delays. There's nothing you can do about that in this incarnation of the measurement. Beginning about 16 bits, the settling silhouette, the profile of the switch coming on, begins to introduce additional time delay errors. And at a part per million, you're out around 240, 250 nanoseconds. A good question at this point might be, how do you know the settling time fixture is trustworthy? How do you test it with something that approximates an ideal input, an ideal DAC? And the surprising answer is, you test it with a read relay. In theory, when these switch contacts open, the voltage settles across this 50 ohm resistor instantaneously. In practice, there are lots of parasitic resistances, capacitances, and inductives in the signal path. They're going to get in your way. and most practical read relays take up on the order of 1 to 2 microseconds to settle to a part per million. However, the Tektronix 109 relay has had very special attention paid to its DC through wideband characteristics and enables you to put in a signal to the DAC settling test fixture that approximates an ideally quick settling DAC. This is the contacts opening and settling macro scale, and on a micro scale you can see about 260 nanoseconds to settle the last couple hundred microvolts, which stands this test fixture in good stead. This presentation has been a heavy distillation of application note 120. You can read a lot more about the details of what we did in that application note at www.linear.com. Thank you for your time.